more about the general flux force equations, which we mentioned in previous slide. Are there any assumptions before we need to know before we using these equations? So the flux and force equation actually is these equations, and in previous slides we showed that we use the linear approximation. When you want to use the linear approximation, there must be some assumption. So what kind of assumption? We take the heat flux J capital Q as an example. In this case, we know the heat flux will be affected by the by different forms of flux applied in our system, including the F capital Q is probably the temperature gradient, and the F small q is the electrical field, and also F1, F2, and so on. So these different forms of driving force will affect the heat flux. And if we want to do this linear approximation, that means, as you know this function, usually we can expand the heat flux JQ with respect to driving force to the first order in Taylor expansion, and we at the near the equilibrium point. Is near, that means it's just a little bit deviated from the equilibrium point. So what's the Taylor expansion? Just remind you that we have a function of x, and this is the Taylor expansion. So we can this fx can be expressed and equals to fx0 plus f prime x0 times x minus x0. If we consider x0 is the equilibrium point, thermodynamic equilibrium point, then you can drop these two terms. Then all you have fx can be directly do this linear approximation, because linear means the partial f partial x, right? And f prime equals partial f partial x, then you times the x. So this is a linear approximation. So here, if we want to use this Taylor expansion on the heat flux JQ, and we just take the F capital Q as an example, what we can do is we do the same thing on this heat flux FQ. It's a JQ. Then you got this, right? And because it is near, F0 actually means the driving force is FQ is at the equilibrium condition, equilibrium point. So this at the equilibrium point, let's know heat flux exists, so you can drop these two terms, and the left term is the JQ prime F0 and times the FQ. So JQ prime actually is a partial JQ, partial FQ, right? And times FQ. So it's if you compare with this term, this is JQ prime, right? So this is so if we do this, we do the same. If we consider other driving force, and you just sum up all driving force as the following, so you will get this one. So the heat flux can be expressed like this: direct drive driven by F capital Q, and in the front we have partial JQ over partial FQ, and we also need to plus, like if there are other driving force, for example like F small q, then that would be a partial JQ partial FQ, right? And this is also the JQ prime, right? Because we do the Taylor expansion on FQ. right? And you can, and so on. So here, if you consider this one, so this one can also be equals to what? Summation of L capital Q and beta, and F beta, and F beta here, beta can be as a capital Q, small q, and 1, 2, and so on, is all driving force applied on the systems. And the front term, this we call the coefficient term, actually is this term. And so if you have a look here, so if we heat flux expressed like this, then we use the beta. So beta can be alpha, right? So if beta equals to alpha, so you got L alpha alpha F alpha plus L alpha beta F beta. So if you compare this, then what you get here would be this term is the L capital Q, right? So it's L capital Q, F capital Q plus L capital Q, small q, FQ, right? So this we call, because the heat flux directly driven by the F capital Q is a temperature gradient, so we call this coefficient as a direct coefficient. And how to explain what's the partial heat flux, partial FQ? What's the direct coefficient? It states that when you apply the unit of FQ, how much heat flux, the change of heat flux of the system. So it's a partial JQ. So when you apply a unit driving force F capital Q, how the change of the heat flux, we call it as a L capital Q, or this is a direct coefficient. And what's this stand for? This actually is a L capital Q, small q. As we mentioned, this small q actually represents the driving force, and the capital Q here is the this driving force contribute on the heat flux. So this is the L capital Q, small q, right? And the physical meaning is when we apply a unit F small q, the change of heat flux, we call it is L capital Q, small q, and this coupling coefficient. Coupling means because the flux which we induced is not directly, is indirect driving, induced by the F small q. So it's an indirect driving force. Usually we call this as a direct driving force, and this and other driving force we call indirect, and the coefficient which we also usually we call it as a coupling coefficient. And I also remarked that what's the direct coefficient, and what's the relationship between the direct coefficient and the coupling coefficient with your materials? This coefficient, no matter is the direct or coupling coefficient, is related to intrinsic material properties. For example, like if we talk about the heat flux, probably will relate it to the thermal conductivity. If we talk about mass transport, probably like J small or Ji, atomic flux will be related to a diffusivity of that material. Yes, so every material have its own direct and coupling coefficient, right? So now if you have for example, this is we call a direct coefficient, right? So even we apply the same temperature on different material 1 and material 2, do you think that will cause the same amount of change in heat flux? Do you think that? No, right? Because the two different material means they do have two different intrinsic material property, or you can say that two different thermal conductivity. So definitely, even I apply the same temperature gradient on them, but they definitely cause the different amount or different changes of heat flux went through this material, right? So that's why I say L capital Q, or this L capital Q small q, this coefficient is related to intrinsic material property. Okay, so the same thing happened on this coupling coefficient, right? Even I apply the same electrical field on two different materials, the changes of heat flux definitely difference, right? So, and these changes were related to material properties. Okay, so in order to explain more details about what's the direct and coupling coefficient, so we summary the relationship between the direct coupling coefficient with your some material properties. For example, like before we talk about this, we need to remember that every material system has its own direct and coupling coefficient, and this coefficient definitely is related to intrinsic material property. But what kind or what type of intrinsic material property, that's we are want to know, right? So following, we just explain what kind of intrinsic material property is related to L capital Q, and what kind of intrinsic material property is related to L small q. So first one we want to show you or demonstrate would be the thermal conductivity kappa. Kappa is related to L capital Q divided by T. And if you want to measure the thermal conductivity, you need to measure that under some boundary condition is no electrical field and no concentration gradient exist in your materials. Then that will allow you to measure the real and accurate intrinsic or thermal conductivity of your materials. The same thing happens on the electrical conductivity. Actually, low electrical conductivity, low is equals to L small q, and you need to measure that under the isothermal conditions. Then following slide is going to explain this kind of show you the relationship between this direct coefficient with the thermal conductivity and electrical conductivity. Then after this, we will move to the other two very famous intrinsic material properties, Seebeck coefficient and Peltier coefficient. So what is the Seebeck coefficient and Peltier coefficient? I don't know if you have some idea about the thermoelectric materials. Thermoelectric material actually is if you apply the temperature gradient on this material, then you will induce the electrical potential gradient. And this electrical potential gradient will drive the current. So you converted the thermal energy to electrical energy. So you can generate the current. So some people use this to as a power supply, something like that. Just the source is a temperature gradient. Then you can light up a LED or something. And this complementary effect we call a Peltier coefficient. Peltier coefficient actually is we supply the electrical current. Then we can use this device to be a heater or the cooler. Why? Because this this materials or this device is going to absorb some heat from surroundings, and in the meantime will release some heat to the surroundings. So at the side with like absorbed the heat, you can use this side as a cooler, because this at this side the heat will always be absorbed by the system. And for the other side, which we call is that we will the heat will be released to the surrounding at that side. For that side can be a heater. So this is we call a Peltier effect. And to evaluate if your material is suitable to be this kind of applications, then to evaluate that we can first of all we can see the Seebeck coefficient and Peltier coefficient. If this value is larger, then probably this materials is suitable to be is one kind of thermoelectrical materials and can be used for thermoelectrical applications. Okay, so let's have a look. Let's move. Let's take a look on the first two. For the first two cases, so the first one is case 1. We question 1 actually A is what is the heat transport in a conductor with a temperature gradient. So now we have a material, right? And material, this is a conductor, and we also observe the temperature gradient apply on this conductor. So how many driving force exist in this system? Only one driving force, right? So because it's only one driving force, and the question asks what's the heat transport, usually asks you heat transport is a J. What's the J capital Q? Because we only have one driving force, so you don't need to mention all driving force because you only have one. And the driving force here is the F, because it only have a F capital Q. So you just write down the J capital Q equals to direct coefficient L capital Q and F capital Q, right? And what's the F capital Q? It's a minus temperature gradient divided by T, right? And next, based on Fourier's law, you know the heat flux equals to minus kappa temperature gradient, right? So if you compare this relationship, you can have some idea about what is the L capital Q is equals to what? K kappa times T. So thermal conductivity equals to L capital Q divided by T. So this is the direct coefficient L capital Q is linear with the thermal conductivity. And let's take a look on the question B. Now we actually is what is the heat transport in a conductor with a temperature gradient? Actually, the question is the same with A, but we do have like in case of open circuit. So what is open circuit? Open circuit actually tell you that there's no current density goes through these materials, these conductors, but there exists electrical field, and the value for electrical field is, as we know, is a minus electrical potential gradient. So what kind of conditions there's exist electrical field but without current goes through this material is something like if you connect this conductor to the voltmeter. Okay, so in this case, can you write down what's the heat flux J capital Q? Because now how many driving force exist or apply on the system? One is we have temperature gradient, surface of the one driving force, and we also have the electrical field. So there are two driving forces. So based on the flux force equation, you need to express like J capital Q heat flux direct driven by F capital Q and direct coefficient L capital Q. Then plus because there's second driving force F small q and times the coupling coefficient driven by F small q contribute on the heat flux. So it's a L capital Q small q here, right? And as we know, the heat flux also need to obey the Fourier's law, so equals to minus kappa prime temperature gradient. I use the kappa prime here. Just want to show you that that's a little bit different with the kappa here, and we will derive and show you that's a different. But as you know, the Fourier's law always is correct. So in this material, even we apply two driving force, you also can measure the heat flux and you know the temperature gradient. You divide it by dividing the heat flux by the temperature gradient, you got the K prime. Okay, then as you know, we can the current density can based on this flux driving force equation. Directly driven by F small q, and this is direct coefficient, and also the coupling, the other driving force is F capital Q and coupling coefficient driven by F capital Q and contribute on current density. And this term, as we know, is an open circuit, so equals to 0. So from this equation, we know the relationship between the F small q and F capital Q, right? And we try to do one thing is we try to substitute this F small q by using this one. So just substitute here. So then we take the F capital Q out, and then we got this equation. And what's the F capital Q? It's a minus temperature gradient divided by T. So we use this to substitute this term. And you got this relationship, and as we mentioned, Fourier's law always correct, so is this Fourier's law minus kappa prime concentration, temperature gradient. So if you compare this, you have one thing. What's the kappa prime? Is equals to this value. This is what? This is a kappa minus one extra term. This term is positive. So this term is positive. So it's a kappa minus a certain term, this value, and equals to kappa prime. So in this case, when the system, there exists two driving force. One is the temperature gradient and also the electrical field. At this moment, if you measure the heat flux divided by temperature gradient, the kappa prime you get actually is kappa, intrinsic material property kappa minus extra term, and this extra term is related to the coupling coefficient and direct coefficient and also the temperature. So if you want to measure the accurate thermal conductivity, please perform your experiments under no electrical field, the condition with no electrical field. Otherwise, you are going to underestimate the thermal conductivity of your materials, because the kappa prime is smaller than kappa, so you are going to underestimate the thermal conductivity of your materials. Okay, so by the way, this case just show you how can we deal with only one driving force and two driving force, and also show you that because different boundary condition, so how can you measure the accurate or correct intrinsic material property? You need to pay attention on the boundary condition when you measure in some material properties. And some people will ask, sometimes the question will ask more, so for example, like what's the entropy production rate for this case? This case, there are only one driving force. So if you what's the entropy production rate per volume? You just times the J, this term, right? J capital Q times the F capital Q. This times this, so it would be, and divided by T. This is entropy production rate per volume for this system. And for this one, the same, right? Although we have two driving forces, but the second one, F small q, is 0. So when you calculate the entropy production rate, you just only have one term, right? It's a J capital Q, is this term, times the F capital Q, and also divided by T. Because the J, we don't need to end it extra J small q, F small q. Because the J small q is 0. 0 times any value is 0. So the entropy production rate per volume for this system must be smaller than in this case. Because what? The driving forces are the same, right? But the flux here is smaller than the J capital Q is smaller than this one, because this is positive term. So K kappa minus a positive term, this K prime is smaller than K. So the entropy production rate in this case would be smaller than in this case. Okay. So let's move to the question 2. Is we have a metal and we connect it to a battery. Battery just implying that there's a electrical field applying this system. So one driving force is electrical field. And what will be the expression of J small q and J capital Q? And can you describe how the apparent electrical conductivity though of this conductor changes in isothermal and adiabatic conditions? So now we have two different boundary conditions. So let's deal with the first one is isothermal. So what's the isothermal tell you? Isothermal, that means the temperature distribution or temperature at everywhere are the same, right? So there's no temperature gradient along your materials, along this metal. And there's no temperature gradient, so do we have a driving force? F capital Q is equals to 0. So for isothermal conditions, only one driving force exists, right? So can you write down the J small q and J capital Q? Yes, try to do that. J capital Q, usually, although just we only have one driving force, but usually I will use the flux force driving force, this equation, to just simply formulate this relationship. And also you can get the current density driven by electrical field, direct coefficient, plus the other possible driving force, temperature gradient term, and coupling coefficient. Because this one, because the temperature gradient equals to 0, so we do have the heat flux flow through our through our metals. Although what? Although there's no temperature gradient, but there's still have heat flux. And how about the current density here? Current density here, although current density, because we drop this term, right? So there's you can get the current density equals to this one. Okay, so we successfully have the expression on J capital Q and J small q. And based on the Ohm's law, you know the current density equals to minus dou electrical conductivity times the electrical potential gradient. This is Ohm's law. So compare these two terms, you know the direct coefficient L small q equals to dou, right? It's the electrical conductivity. Okay, so what's the adiabatic conditions? Adiabatic conditions in thermodynamics actually is just told you there's no heat flux in the systems, so the J capital Q is equals to 0. So based on this this relationship, this results, the same you can formulate the heat flux J capital Q like this, right? And because in a diabetic condition, so the heat flux equals to 0. So you will get the relationship between the F capital Q is a minus temperature gradient divided by T, and equals to this one is related to the electrical potential gradient, right? So as long as you get this relationship, so let's take a look on the current density part. Current density can also be expressed like this, right? And we try to substitute which one? We try to substitute this term with this one. So we can take the potential gradient minus potential gradient out, then we can guess. Then also the Ohm's law always is correct. So minus low prong electrical potential gradient. So you compare these two terms, then what you get here, the low prong, you measure the electrical conductivity you measure in this system will be equals to L small q minus this term. And this is the low, right? So low prong actually is low minus extra term. This extra term actually is positive. So the low prong here is what you measure in a diabetic condition. You measure the current density directly divided by the electrical field, then you got a low prong. This low prong actually is smaller than the low, which is intrinsic electrical conductivity of your materials. So that's what we get here. So if you measure the electrical conductivity in a diabetic condition, you are going to underestimate the electrical conductivity of your materials. Okay, this definitely is smaller than low. So if you want to measure the electrical conductivity, please, you need to perform these experiments or measurements in isothermal conditions. So the boundary condition matters because that will affect the intrinsic material property you measure. If the occurrence of intrinsic materials you measured. So based on this, you know, when you want to measure the electrical conductivity, please perform that under isothermal condition. That actually just implying that you need to make sure that there's no other driving force exist in your system except the driving force which drive the property. Which related to the flux you want to measure or learn about that. So for this case, because you want to measure the electrical conductivity, so electrical conductivity is related to you need to measure the current, right? So the only possible driving force existing in your system can only be the electrical field. If there are other driving force exist, for example, like temperature gradient or other concentration gradient, something other driving force, that definitely will affect the current density you measured, because they definitely contribute some amount on the current density that will cause the error in your measurement. The same thing happened in previous case. In this case, you are going to measure the thermal conductivity, which is and by what? By measuring the heat flux divided by temperature gradient you apply on this system. So if there are other driving force applied in this system, for example, like electrical field, concentration gradient, and so on, that definitely contribute some amount of heat flux that will affect the heat flux, no matter it's increase or decrease, but definitely affect the value of the heat flux by coupling coefficient. So the thermal conductivity you measured definitely is not the correct value for your interesting materials. Okay,